Find the optimal reservoir release. In this problem, a reservoir with an initial volume of 100 units is to release a certain quantity of water to meet a downstream demand. That downstream demand will be between 70 units and 80 units with a uniform probability distribution. The cost to release 1 unit of water is 1, and the penalty of not meeting the demand is equal to 2, and there is no penalty for oversupply. The objective function for this stochastic programming problem is to minimize the sum of the quantity of water released from the reservoir and the sum of the penalties for not releasing exactly the target demand, where the shortage equals the maximum of 0 and the demand minus the release, and the surplus equals the maximum of 0 and the release minus the demand. Next, we can plug in the given values for release cost, shortage penalty, and surplus penalty. The constraints for this problem include the volume constraint, where the quantity released, X, cannot exceed the initial volume of 100 units. To put this constraint into standard form, we'll change X to X1 and add a surplus variable, X2. Now the inequality constraint is an equality constraint, and the unit cost associated with the slack variable X2 equals 0. The second constraint is the demand constraint, where the quantity of water released plus the shortage minus the surplus equals the demand. Lastly, all of the decision variables must be non-negative. An initial feasible solution would be to release 0 units of water and allow the shortage to equal the demand. In order to know the direction and magnitude to adjust our current reservoir release value, X1, we'll formulate a problem B, which is to minimize C transpose minus pi chi of I times T all multiplied by X hat, where the same constraints from the initial objective function also apply to problem B for X hat. In equation Z hat, pi chi of I equals the shortage penalty times the probability shortage will occur, minus the surplus penalty times the probability a surplus will occur. The problem statement provided the penalty values, which can be plugged in. Next, we'll define vector T such that Tx equals the production, or total supply, chi. Since 100% of X1 contributes to the supply and 0% of X2 contributes to the supply, vector T is 1, 0. From our initial conditions, vector X is 0, 100, which makes chi equal to 0. Since we know the demand ranges between 70 and 80 units, there is a 100% probability the demand will be greater than 0, and a 0% probability the demand will be less than 0. This equation reduces to 2 times 1 minus 0 times 0. So pi of chi I is currently 2. Plugging in the other values into problem B, objective function, simplifies to minimize negative x1 hat. From the constraint set, we know x2 hat must be non-negative. Therefore, the maximum value of x1 hat is 100 units, and the minimum value of z hat of x equals negative 100. We'll use the values of x hat later in the problem. Back to the original objective function, we'll develop a curve for the objective function z of x to determine what release value, x1, minimizes the objective function. From before, we can divide the objective function into two parts: the cost of water and the penalty from shortage or surplus. If we focus in on the cost of water, we calculate the cost to be 1 times x1, which is a linear relationship. Next, we'll focus on the penalty term and rewrite the penalty term as Q of chi I xi I. Since the demand distribution ranges from 70 units to 80 units, we'll calculate the penalty for 3 different regions for x1. Region A will be for x1 at most 70 units. Region B will be for x1 at least 70 units and at most 80 units. And range C will be for x1 at least 80 units. We'll begin by calculating the penalty for region A. QA equals the shortage penalty times the shortage if supply is less than demand, or the penalty equals the surplus penalty times the surplus if supply exceeds demand. Plugging in the values for the penalties, shortage, and surplus, and knowing that for region A, x1 will be less than xi, the penalty for region A equals 2 times the shortage. Since the demand is defined by the distribution between 70 and 80 units, the penalty for region A is the integral of the product of the penalty for a given demand times the probability of that demand occurring. After a few steps of calculus, we compute the penalty to be 150 minus 2 times x1. Next, we'll define the penalty for region B. As with region A, the penalty for region B only occurs if the release, x1, is less than the demand, xi. Therefore, the first integral can be removed from the penalty equation. Next, QB is calculated in terms of the release, x1, and the probabilistic demand, xi. The penalty in region B equals 0.1 times x1 squared minus 16 times x1 plus 640. Lastly, the penalty for region C is calculated and equals 0, because the surplus multiplier, Q minus, equals 0. Returning to the objective function, C transpose x is equal to x1, and the penalty term, Q, depends on the region, A, B, or C. Once plotted, the curve is linear in regions A and C, and quadratic in region B. Clearly, the optimal solution is within region B. Therefore, we'll preserve the equation for region B and update our x vector, where the new x vector, x tilde, equals lambda times the current x vector plus the quantity 1 minus lambda times x hat, where lambda is a non-negative real number strictly less than 1, and x hat is the optimal x vector from problem B, solved earlier. If we expand the equation out and plug in the values for x and x hat, we can solve for x tilde in terms of lambda. x1 tilde equals 100 minus 100 times lambda, and x2 tilde equals 100 times lambda. Next, we'll plug in this new value of x1 tilde into the objective function for region B. Solving for z as a function of lambda, we get z equals 1000 times lambda squared minus 500 times lambda plus 140. If we set the derivative of zb of lambda with respect to lambda equal to 0 and solve for lambda, we compute lambda equals 0.25. Now we can revisit our equation for x tilde, and after plugging in 0.25 for lambda, x1 tilde equals 75 units and x2 tilde equals 25 units. After an additional iteration, lambda equals 0, indicating this current solution is optimal. When reviewing the possible solutions, the answer is C.